November 8th, 1942. The dawn breaks over the beaches of North Africa, signaling the start of Operation Torch, the first major American amphibious assault of the war. But for the men of the 1st Infantry Division, huddled behind the fragile cover of sand dunes, the sunrise brings not hope, but an industrial horror that military planners had feared for a decade. The ground begins to tremble, a rhythmic, mechanical earthquake that vibrates through the boots of every GI. Over the crest of the desert horizon, they appear. German Panzer IVs, steel leviathans thundering across the sand, their long 75mm guns swiveling with robotic, predatory intent. To Private First Class Robert Watson, clutching his M1 Garand rifle in the dirt, the situation is mathematically hopeless. He looks at his rifle, then at the 25-ton monsters approaching at 25 miles per hour. He knows with terrifying clarity that his .306 caliber bullet, a marvel of small arms engineering, will simply shatter like glass against the 50mm face-hardened steel of the enemy. The standard American 37mm anti-tank guns, nicknamed squirrel rifles by cynical crews, are already firing, but the shells are ricocheting harmlessly off the German glossy plates, sparking into the sky like fireworks. This is the tank terror in its purest form, the realization that the infantryman has been sent to a gunfight armed with nothing but a pocket knife. As the panzers close the distance, crushing the scrub and sand, the morale of the platoon begins to evaporate. They are facing the apex of the Blitzkrieg war machine with zero capability to stop it. But what Private Watson and the terrified men on that beach do not realize is that the balance of power is about to shift forever, thanks to a strange, clumsy-looking metal tube strapped to the back of Sergeant Miller. It looks less like a weapon and more like a piece of salvaged plumbing, a stovepipe with a wooden stock and a crude optical sight. It has no recoil mechanism, no heavy carriage, and it fires a projectile that seems laughably slow compared to a tank shell. However, this device, designated the Launcher Rocket AT-M1, represents a secret that Allied intelligence has guarded with paranoid intensity. It weighs only 13 pounds and costs the U.S. government less than $43 to manufacture. Yet it possesses a dark magic that defies the conventional laws of ballistics. Inside its warhead lies a physics anomaly capable of punching through more armor than an artillery piece weighing 50 times as much. The German tank commanders, peering through their periscopes, see only soft infantry targets. They have no idea they are driving into a trap set by a man who is not a soldier, not a general, and not even an American by birth. The architect of their destruction is Henry Mohapt, a Swiss chemist whose background was in farming and mining, not war. And in the next few seconds, his agricultural experiment is going to turn the invincible German Panzer into a burning iron coffin. September 1, 1939. As the 1st German Panzer divisions tear across the Polish border, the world witnesses the terrifying debut of Blitzkrieg. For military observers in London and Washington, the campaign is a brutal awakening. In just 18 days, the highly mobile German armored formations dismantled the Polish defense, rendering traditional anti-tank tactics obsolete. The carnage proves that modern warfare now belongs to whoever possesses the most efficient mobile steel. The Allied crisis, however, is not just a lack of tanks, it is a fundamental crisis of physics. At this stage of the war, anti-tank doctrine is enslaved to the kinetic energy rule. To penetrate thick steel, a projectile must travel at incredible velocity and possess massive weight. This chemical-physical requirement dictates the design of weapons. The British 2-pounder anti-tank gun, though capable, weighs nearly 1,900 pounds and requires a dedicated truck to move. Once deployed, it is a static target. If the panzers flank it or close the distance too quickly, the gun crew is doomed. The mathematical reality is devastating. To stop a 20-ton tank, an army needs a 2-ton gun. For the infantryman on foot, this means he is effectively defenseless against armor, trapped in a tactical paradox where the shield has become so strong that the only possible sword is too heavy to carry. In Washington, Colonel Leslie McNair, the chief architect of U.S. ground forces, stares at reports from the European theater with growing dread. The American 37mm anti-tank gun, the pride of the infantry, is revealed to be a pea-shooter against the updated German Mark III and IV. At standard combat ranges, the American shells simply shatter upon impact. The scientific community is scrambled to find a solution, but the ideas range from the impractical to the absurd. Dr. Charles Lawrenson at Caltech proposes electromagnetic railguns, but they require massive electrical generators that are impossible to move through mud or sand. The prevailing expert consensus is bleak. There is no such thing as a lightweight tank killer. Every ounce of armor added to a panzer requires 100 pounds of steel and explosives in an anti-tank gun to counter it. The industrial capacity required to match German armor with heavy guns exceeds even America's massive manufacturing power. Just as the Allied command prepares to accept that the age of the foot soldier is over, a dossier arrives from an unlikely source. It speaks of a hollow charge experiment in Switzerland that supposedly defies the laws of ballistics. The experts scoff, calling it a laboratory curiosity. But as the panzers prepare for the invasion of France, the armor paradox is about to be challenged by a man who views explosives not as a hammer, but as a scalpel. The man destined to shatter the German panzer's invincibility was not found in a prestigious military academy, but in a modest chemical-scented laboratory in Zurich. Henry Mohaupt, born Heinrich Mohaupt in 1915, grew up in a household where explosives were a common trade rather than a weapon of war. His father was an industrial chemist specializing in mining, and young Henry inherited a pragmatic, farmer's approach to science. In late 1935, while the rest of Europe was obsessing over bigger cannons and thicker steel, the 20-year-old Mohaupt was focused on the mundane task of improving rock blasting techniques for Swiss mining companies. He wasn't trying to kill tanks, he was trying to find a way to fracture hard ore deposits more efficiently without damaging the surrounding tunnels. The eureka moment occurred during a routine experiment when Mohaupt decided to line a small explosive charge with a simple copper cone. Standard explosive physics suggested the blast would expand outward in all directions, losing most of its energy to the atmosphere. Instead, Mohaupt witnessed something that defied every ballistic textbook of the era. The copper cone collapsed under the pressure of the explosion, focusing the energy into a needle-thin, hypervelocity jet of molten metal. When he examined the test target, a thick steel plate, he found a perfectly round hole burned through it as if it were soft butter. This phenomenon, now known as the Monroe effect, had been a laboratory curiosity since 1888, but the academic world had dismissed it as a useless anomaly with no practical military application. But Mohaupt, however, saw the staggering potential that the university-trained men in suits had missed. He realized that this focused explosive jet did not rely on the speed of the projectile or the size of the gun. It relied purely on the chemical energy within the charge itself. This meant that a 2-pound device could theoretically achieve the same penetration as a 2-ton anti-tank gun. Working alone in 1936 and 1937, Mohaupt began a series of dangerous, unauthorized experiments. He melted down scrap copper pipes in a makeshift furnace, hammering them into precise conical liners with the patience of a Swiss watchmaker. His notebooks began to fill with revolutionary calculations. If he could stabilize this jet, he could give a single man the firepower of a heavy artillery battery. But as he looked at the crude, hand-hammered devices on his workbench, he faced a new, daunting reality. He was an outsider, A civilian with no military credentials trying to sell a magic solution to an establishment that believed only in the brutal logic of heavy kinetic steel. By 1937, Henry Mohout's laboratory was a sanctuary of revolutionary physics, but the world outside was a fortress of bureaucratic arrogance. Armed with his hand-hammered copper cones and data that defied conventional ballistics, the young Swiss chemist began a grueling journey to convince the military elite of Europe. His first stop was the Swiss military authorities, where he expected his countrymen to embrace a domestic solution to the growing German armored threat. Instead, he met Colonel Hans Frick, the chief of Swiss Ordnance Department, a man whose mind was as rigid as the steel he studied. Frick watched a demonstration of Mohout's charge burning through a railway rail and simply shook his head. To Frick and his contemporaries, Mohout was a magician performing a parlor trick. Established military doctrine dictated that armor could only be defeated by kinetic energy, massive shells fired at high velocities. Frick's verdict was cold and final. Mr. Mohout, the Swiss Army requires proven weapons, not exotic devices that contradict the laws of science. This rejection was not based on failure, but on the terrifying possibility that a civilian amateur had rendered decades of professional military engineering obsolete. The rejection in Switzerland was only the beginning of a humiliating tour across Europe. Mohout traveled to Paris, seeking an audience with French weapons experts as the shadow of the Third Reich lengthened over the border. The French response was even more devastating. Their experts dismissed the hollow charge concept as a violation of the fundamental principles of ballistics. Major Geoffrey Williams, representing the British Royal Arsenal, viewed the crude prototypes with barely concealed contempt, suggesting that such laboratory experiments would fail catastrophically in the mud and chaos of real combat. The technical establishment's wall of silence was unanimous. Every major military power believed that if the solution to the anti-tank crisis was as simple as a 2-pound explosive charge, their own scientists would have found it years ago. When German forces finally overran France in June 1940, Mohout found himself stranded in neutral Switzerland, his primary development opportunities extinguished, and his revolutionary technology unwanted. He faced a crushing choice: abandon his discovery or find a way to the only power left with the industrial scale and the desperation to listen: the United States. October 18, 1940. Under a gray, overcast sky at the Aberdeen Proving Ground in Maryland, the future of American infantry warfare stood on a folding wooden table. Henry Mohout, having finally navigated a labyrinth of visas and bureaucratic delays to reach American shores, felt the weight of every skeptical eye upon him. Surrounding him was the pinnacle of the U.S. military-industrial complex: Colonel Rene Studler, Chief of Army Ordnance Research, and Dr. Clarence Hickman, the nation's leading authority on ballistics. The atmosphere was thick with professional disdain. To these men, who spent their lives perfecting the massive muzzle velocities of heavy artillery, Mohout's collection of modified mining charges looked like children's toys. Dr. Hickman, leaning forward with visible irritation, voiced the room's consensus. "Shaped charge effects are a known laboratory phenomenon, Mr. Mohout. Our researchers concluded years ago that they offer no practical battlefield application. Why should we waste the War Department's time on theories that professional experts have already dismissed?" Mohout didn't argue. He simply prepared his improved prototype, a small, unassuming cylinder of explosive energy, and aimed it at a thick slab of naval armor, the kind of steel that would normally require a 75-millimeter field gun to even dent. The explosion was not the thunderous roar of cannon, but a sharp, high-pitched crack, followed by a brilliant orange flash. As the acrid smoke cleared, the skepticism in the room vanished into an eerie, heavy silence. The observers crowded around the target plate and found a perfectly round 3-inch hole drilled entirely through the massive steel slab. The penetration exceeded the performance of the Army's standard 37mm anti-tank gun by a factor of 3. Dr. Hickman broke the silence, his voice now devoid of condescension. This represents a fundamental breakthrough in anti-tank capability. Suddenly, the room erupted into a fierce debate between the traditionalists and the visionaries. While some scientists argued that this exotic physics was too unstable for mass production, Colonel Robert Goddard, the father of American rocketry, stepped forward. Goddard, who had spent decades being mocked for his own impractical ideas, recognized the genius in Mohop's work. His endorsement was the final hammer blow. General Campbell, realizing the German Panzers were currently invincible to his troops, turned to the Swiss chemist with a grim smile. Mohop was granted unlimited resources and top priority classification. The American gambit had begun. The U.S. Army was officially betting its survival on a farmer's explosives. By June 1942, the desperate laboratory breakthroughs at Aberdeen had to be forged into a weapon that a scared 19-year-old could carry into a muddy trench. The challenge was a technical nightmare. Mohop's shaped charge was devastating, but it had no way to reach its target. If fired from a traditional gun, the high-pressure propellant would crush the delicate hollow cone before it even left the barrel. The solution came from an alliance of outcasts. Colonel Leslie Skinner and Lieutenant Edward Ull, working in a secluded workshop, realized that the warhead didn't need a heavy cannon, it needed a rocket. They jerry-rigged a simple steel tube, literally a hollow pipe, and fitted it with a shoulder stock and a battery-powered ignition system. This was the technical thriller of 1942, a race against time to stabilize a rocket-propelled grenade that experts claimed would be more dangerous to the shooter than the tank. Lieutenant Ull, acting as his own test pilot, held the prototype tube, a device that looked more like a piece of salvaged plumbing than a revolutionary weapon, and fired it at a captured German Panzer IV. The rocket roared out of the tube with a backblast that scorched the grass, and seconds later the German tank's turret was engulfed in a secondary explosion as its ammunition ignited. The stovepipe had worked. The weapon's official birth was as unconventional as its design. During the final demonstration at the Florida Desert Ranges, the device still lacked a name. As General Barnes and other top brass watched the lightweight tube dismantle heavy targets, someone remarked that the strange metal pipe looked like the bazooka, a comical telescoping musical instrument played by radio comedian Bob Burns. The name stuck instantly, a humble label for the most lethal infantry innovation of the century. But beneath the funny name lay a masterpiece of industrial simplicity. Unlike the German Panzers, which required thousands of man-hours to build, the bazooka was designed for the American system. It was cheap, it was light, and it could be manufactured by any factory that made steel pipes. However, the bureaucracy wasn't finished fighting back. Traditionalists still argued that a 13-pound tube couldn't possibly replace a 2,000-pound anti-tank gun. They tried to bury the project in additional testing and safety concerns. It took a direct, aggressive intervention of General George Marshall to bypass the red tape and order 5,000 units for immediate shipment to the front lines. The bazooka was no longer a secret experiment. It was a mass-produced reality, heading straight for the beaches of North Africa, where the German Panzers were waiting, unaware that their reign of invincibility was about to end. The tank terror that had paralyzed Allied infantry since 1939 was finally shattered in the dust of Tunisia and the rocky hills of Sicily. As the first M1 bazookas were unleashed during the North African campaign, the German Panzer crews experienced a psychological trauma they were entirely unprepared for. For years, a panzer commander like Hauptmann Rudolf Schmidt felt invincible behind 4 inches of hardened steel. Infantry were merely targets to be overrun. But during the fighting near Oran, the reality changed in a single, blinding flash. A German Panzer III was advancing confidently toward an American foxhole when a small hissing rocket streaked from a clump of scrub. The shaped charge warhead struck the turret ring, and the hypervelocity copper jet, moving at 20,000 feet per second, drilled through the armor as if it were parchment, igniting the fuel and ammunition within milliseconds. The tank didn't just stop, it disintegrated. This was the shock on the battlefield, the moment the German High Command realized that the most advanced fighting vehicles in the world were now vulnerable to a weapon that cost less than a soldier's monthly salary. Reports began flooding into Berlin about American rocket men who could turn every bush and ruin into a deadly anti-tank nest. The culmination of this technological revolution occurred during the Sicily campaign in July 1943, when the bazooka faced its ultimate predator, the Tiger I. At Gala, Staff Sergeant Charles Kelly faced a 57-ton monster with 100 millimeters of frontal protection, armor that no Allied tank gun could reliably penetrate. Armed only with his M1A1 stovepipe, Kelly waited until the Tiger exposed its flank. The first rocket shattered the massive track, immobilizing the beast. The second rocket punched directly into the turret, killing the crew and sending a geyser of flame through the hatch. The commander of the German division, Oberstleutnant Hans Kluge, was so stunned by the loss that he issued an emergency tactical revision. American infantry weapons now pose a greater threat to our armor than enemy tanks. The German response was the ultimate form of flattery and desperation. They immediately began reverse engineering captured American bazookas to create their own version, the Panzerschreck. But the damage was done. The invincible aura of the Panzerwaffe had been burned away by Henry Mohopt's focused fire. Every American GI now carried the power of a heavy artillery battery on his shoulder, and for the first time in history, the man on foot had become the hunter, and the tank had become the prey. By May 8, 1945, as the echoes of gunfire faded across a shattered Europe, the verdict of history on the bazooka was written in the twisted, scorched hulls of the Panzerwaffe. Captured German documents revealed a staggering reality. Over the course of the war, the Wehrmacht had lost more than 15,000 armored vehicles to infantry-carried weapons. Henry Mohopt's agricultural experiment had managed to destroy more armor than Allied tanks and anti-tank guns combined. The production numbers were equally mind-boggling. American factories had churned out over 20 million bazooka rockets, a deluge of precision munitions that democratized the power of destruction. Even the highest-ranking German officers, like Field Marshal Gerd von Rundstedt, admitted in declassified debriefings that the bazooka had forced a complete revision of their doctrine. The iron wall of the Blitzkrieg had been dismantled not by a larger army, but a 13-pound tube that turned every American squad into a lethal anti-tank unit. The Swiss farm boy, who had been mocked by university elites, had effectively ended the era of heavy armor could dominate the battlefield with impunity, proving that in modern warfare, the most powerful weapon is not the thickest plate of steel, but the most innovative application of physics. The story of the bazooka did not end in 1945. It evolved into the DNA of every modern conflict. Henry Mohopt eventually moved to Santa Barbara, California, where he lived a quiet, unassuming life, rarely mentioning that he was the man who had terrified the Third Reich's generals. However, his legacy of fire continues to protect soldiers on every contemporary battlefield. From the RPGs of the Cold War to the sophisticated Javelin and NLAW missiles used in modern-day Ukraine, the fundamental principle remains the same. The hyper-velocity-shaped charge jet pioneered in a makeshift Zurich lab. The mathematical elegance of Mohopt's discovery allowed the foot soldier to maintain his relevance in an age of increasingly complex machinery.
When a modern soldier fires a lightweight missile and watches it pierce the most advanced composite armor in the world, he is utilizing the rebel chemistry of a Swiss civilian who refused to believe in the impossible. Henry Mohaupt proved that revolutionary solutions often come from the most unexpected sources, and his legacy remains a testament to the fact that ingenuity, when focused like a molten jet, can cut through the strongest obstacles history can build.